Is it okay to maybe turn off the light? Yeah, this would be great. Yeah, thanks for the introduction. Yeah, the title is pretty ambitious. Yeah, so yeah, I want the content something worth to the title. So yeah, before starting the main content, I really want to appreciate to my collaborators and my fantastic students in Rutgers Machine Learning Lab. And what I will be presenting here is actually what they did. So I'm just delivering that thing. And I have some collaborators here, and these are some also collaborating companies. Yes, so we all know that deep learning has achieved really remarkable results. So some of the technology can now be used in very successful commercial systems, and also we achieved superhuman level performance in many areas, like game playing, and also some set of image recognition tasks the actual AI system does better than human. So, but we know that this technology has many limitations still. It works on some limited tasks, limited domain pretty well, but in general, it especially from the perspective of general intelligence, like a cognitive science kind of perspective, it has many limitations still. So for example, this is the chatbot made by Microsoft, and it is designed to learn from the replies of the humans, and it learns some wrong replies, and it doesn't have any kind of ethical sense, so it actually generated this kind of sentences. And also this is actually stop sign, but actually if we can manipulate the learned model with some trick, then actually we can make the learned system recognize make fully long decisions. So this is a stop sign, but the machine learning model actually, with this little bit of manipulation of the observed image, it actually misunderstood this as a speed limit sign. And also this kind of classification is very easy to us humans, a very intuitive thing, but also the AI system can make a very wrong decision for this thing. And this is an example of a scene understanding. So the task is given an image, the AI system needs to generate the description about that scene. And what it generated here is an airplane is parked on the tarmac at an airport. So the AI system recognizes this as an airplane that is parked. But for we humans, this is never possible because the conclusion is that the current AI system, the way it makes the decision is pretty different what we humans do, right? So why this deep learning system make this kind of wrong decision? So it seems like not really making deep understanding, right? It's deep learning, but its decision seems not pretty deep. And one thing I want to say here is I'm not talking about the whole deep learning area. Actually, there is some research part that they try to deal with this problem already. But I want to say weak deep learning that actually has this kind of severe problem. So one answer why this kind of problem happens is we could say, and broadly, we could say the system doesn't have a common sense. Then we could ask, what is common sense? So this is my definition. So I'm not sure, I haven't looked into the Wikipedia definition or other definition, but it seems like pretty reasonable to say that it's kind of general knowledge about how the world works, and that is kind of obvious to most of the people. And what it means by how the world works, if you go to a bit more in detail, it could be something like this intuitive physics, how the objects behaves and interact, and also about intuitive psychology, how the agent, which has some kind of intention, behaves and also interact. So this could be understood how objects and agents behave and interact in this kind of physical world, maybe where time and space govern some kind of under some rules, can be seen as a more specific description about common sense. So we could say current AI system currently doesn't have this kind of, can't really understand this kind of things. So why current weak deep learning system, or why current AI technology cannot understand this kind of knowledge. Why it cannot have this kind of knowledge? So the reason I see is, I think is most of them are current technologies based on supervised learning, and because of that, it doesn't need to learn actually the model of the world. Without modeling how the world works, it can just work with the thanks to the supervision. So I really think that the human supervision used in the current AI system is the evil. So that's the start of the everything became wrong from that point. The reason is if you use supervision to make the learning system learn faster or easily, then it basically makes the problem first solvable while skipping learning the general structure of the world. So because we provide the label already, the system doesn't need to learn actually how the world works. For example, if you see a baby, before the baby learn to how to classify what is chair and what is pizza, it first needs to learn the general knowledge about the world. It needs to learn what is object, what is moving thing, and what is agent, the distinction between object agent. After spending many months to learn this kind of general knowledge, after that it can try to do something like classifying specific object, things like that. But if we provided the label, supervision label, it doesn't need to do that, because it can skip all these processes because we are given directly what it needs to do. And the second point is related to the first one. So because of this supervision provided, the problem can be defined in a long way. Because we already provide the supervision, the data doesn't need to include maybe temporal information, or it doesn't need to be capture the three-dimensional space. So, for example, the famous data set, the ImageNet image recognition task, it's image classification task. It only shows a picture of this thing, laptop. And the task is given the one perspective of the picture, it needs to predict the class of the laptop. But we humans, laptop is not just this kind of set of pixels. This is like an interactable thing, and we can see 3D perspective of the thing. So that's real knowledge about what it means by laptop versus to humans. But if we provide that supervision, given picture, this is a laptop, then the classifier doesn't need to learn that kind of general knowledge about the world. So the models and the representations learned in this way is now showing pretty shallow and fragile behavior, like the examples we saw in the previous slide. And the conclusion here is the task currently, or the objective function, is simply designed in a wrong way that doesn't need to learn the model. Okay, then if this supervised pattern recognizer, if it is not the right task to learn the model, then what is the right task we need to design to enforce the learning model, machine learning model to learn the world? So this is the task not only me, it is claimed by some also cognitive scientists as well. So we need to learn to build the model of the world. So it's not solving only some specific narrowly defined task like a speech recognition or image classification. We need to learn the world itself, how to build the world. Not only this world, if we are given a new object or agent, we need to have the ability to build the model of that new things. So I think this can be done. If we really have this kind of model, then we can actually ask some high-level cognitive questions to this model. For example, we can ask question like about the future imagination. So for us, it's pretty easy ability to imagine the future. What would happen after 1 hour? I will giving this talk, and after this talk, I will have some meetings or something like that. So because I have in my brain the model of the time and space and people, agent to object, and I'm keeping tracking of what's happening, that kind of stream of events. So that's kind of the model in my brain. So if you have that thing in the machine can also do future imagination. And the second cognitive question we could ask to the machine is causal questions. So we humans also can answer very difficult questions about, for example, what if there is no sun tomorrow? So this thing is not something we can experience. We cannot collect data set, right? We cannot collect, but we can still do inference about this extreme case of the question. So this kind of question, if we have the real model of the world, then we can do this. And these are mostly, I think, unsupervised tasks that are pretty difficult, if impossible, not impossible, to solve without learning the structure of the world. Yeah, so without this kind of core structure, yeah, it seems pretty hard. And by this kind of a core structure, what I mean more explicitly, it can be for example, some special temporal causal graph, and where the node can be some agent and object, and the relationship between these nodes and agents can be the physical or psychological relations. So if we can have this kind of core structure, if we can learn that structure from low sensory images, then we can use this kind of structure to do this kind of future imagination and what if questions. So this is kind of big, the task I think we need to build to solve the problem. And yeah, in this talk, what I'm talking is pretty, in machine learning area is pretty broad. Some people working on for some specific application performance improvement, and some other people works on more like a general intelligence thing. So it could be seen like this narrow AI or narrow deep learning try to solve each of the problems. So we are given problem, for example, maybe improving the speech recognition performance, and we have a system for it, and we have another system for machine translation or image recognition, things like that. So currently what we are doing, the innovations happened pretty much in this way. So we have different solutions, and this solution works for that specific task or domain really well. But it's showing some problems because this has really narrowly defined world. And if we ask some more generalized, some question that needs to maybe a little bit extrapolate from that world, then the system we see totally fails. So the task I introduced in the previous slide is actually the solution, I think, is we need to first learn how to build the world model from different problem settings. And from this world model, I mean, it should not, it ideally should be learned without supervision or unsupervised way, or in other way, in a self-supervised way, which is what we humans mostly do. And after, if we have this kind of world model, then we can provide a little bit of supervision, or even without supervision, the task can learn a new task pretty easily. So this is the kind of illustration of the thing. Yes, so then, yeah, it's important to learn, what I'm claiming is it's important to learn the world model, not only the world model, important to learn its core structure of the model. And how can you learn that core structure? What's the important property of that core structures? So first, I think, as I have been kept saying, is it should be unsupervised. So if we provide supervision, that's, I think, a really, really long thing. And we can provide later the supervision, but in the while, it's like, so another analogy is current AI system is like it can do calculus, very advanced calculus, because you don't need to provide the data set of calculus, but it doesn't have the ability to do algebra. So, but we humans, I mean, we learn algebra first, and the calculus is part of the solving algebra calculus. Solution is from the understanding of the algebra, but current system doesn't have that thing. So to do this kind of proper curriculum learning, we should do self-supervised learning or unsupervised learning in the early stage of the learning. Yes, and also that learning should focus on some modular entities, such as object and agent and relationship among these entities. And these modules, the reason is, I think learning this very complex world by putting that data into one very large neural net doesn't really make sense. We need to modularize so that we have to learn modularized independent modules and then let them be somehow composited to model more complex thing. Otherwise, it will not scale or it will not generalize to different situations. So I will show you some examples of this kind of thing. And actually, another important point is, for my research, I don't want to do this object or agent-based learning with the annotations. For example, given an image, I want to use only this low sensory input. I don't want a human already label, this is object, this is chair, so I don't want to use that thing. So this raises the problem of learning the concept of object and agent, their relations only from low sensory images. And then time and space. So most of the relationship important concepts we could learn this kind of structure is governed by time and space. So that is very important part. For example, that image I showed you, like the airplane parked in something. So if you think what the thought process was happening in my brain, actually I think it's wrong because I see with that pose of the plane, I see it was flying and what has happened in the past and what will happen in the future. So in my brain already the video is playing, right? But with the supervision, we are asking the AI machine to make the generation only from one frame of the image. So that's the problem of not considering time and space. So this kind of thing is not my own view. Actually, it is discussed by some cognitive psychologist already, and she claimed that this kind of core knowledge is already built in human brain at birth. So what's the so until now it's pretty high level and problem setting and motivation and direction and so on. But I want to build this kind of system using machine learning method. So the framework I use to do this is deep generative latent variable modeling. Here, this is a tool where we can do unsupervised learning. And we can learn structured representation, and we can also learn to render or generate the observations. So the simple model looks like this. So our eventual goal is to learn the distribution of the observation X, maybe some images, and this theta is the parameter of the model. And we assume that this observation is generated from some kind of hidden latent actual factor representation or structure, low dimensional real structure. And given that structure, actually we are generating this scene. For example, for about this scene, actually this jet can be each person, like some symbolic representation, and it may have some relationship, like some people on top of sitting on some chairs, things like that. That kind of high-level thing. But X doesn't have that information. X is actually the full image. It's just a matrix of pixels, right? So that is what this model tries to explain. Yes, so how to learn using this generative latent variable models. So in modern machine learning, in deep learning, what we are using is this model. So if we write this expression in some way, actually we can obtain this kind of term and some additional term. But here, what we are doing is actually we have the input X. We can think this as an image, and from the input we generate actually the structure, the representation Z. And given that generated representation, we try to decode it to the original image. So here the high-level idea is, if this representation Z is really core and expressive, good representation of what is observed, then this decoding process should reconstruct what is provided as the input, right? So this is the encoder and decoder, and there is some information bottleneck kind of concept in the middle that is compressing the whole high-dimensional image into maybe 10 or 20-dimensional latent variable. Then this 10 or 20-dimensional latent variable, the structure should explain the really discarding every minor thing, but it should express really core thing like some structure, maybe what and where, pose, color kind of things, right? So this is the architecture. So we call this part getting representation jet as inverse graphics, because graphics, if you think graphics engine, you program this thing, what, when, where, and pose this thing, and it actually generate the scene, right? So this is graphics, but this is what is doing is actually inverse of the graphics. We obtain the image, and from there we try to extract the core structure of the observation. And this is one most popular model that instantiating the previous model, which is called variational autoencoders. And here we learn this model by backpropagation, and here the latent variable jet is represented as just a set of, just as a continuous vector. So there is no really structure, right? Here we don't have, it's really hard to get the what and where, color, this kind of information. So this is the thing, and my goal in the in the later slide, I will introduce some models. We actually here, this part, we try to learn very structured and interpretable representation of the world without any supervision. The only supervision is, it's not really supervision, but we only use the observation. Okay. So in the following, I will introduce 5 or 6 models we've been worked recently, and each of this model combines some interesting aspects of this physical world, object and space, time, agent and relation, and so on. So we don't have a final eventual model that combines everything yet, so we are going to that direction, but these are kind of solving part of the problems. Okay, and one comment I want to have is actually we submitted pretty much of this work into machine learning conference, and some reviewers complained that compared to what computer vision has been done, is what we've been doing looks pretty toyish. But here I want to emphasize that, yeah, in computer vision we are making this kind of beautiful segmentation and object detection thing, but these are all very hardly annotated system. So every human does segmentation for every people, every car, and make bounding boxes. This is kind of the learning system learned through that heavy annotations. But what I'm doing here is it's a fully unsupervised vision thing. So it's a very early stage, but it's definitely very interesting area. So the first system here, we want to develop a model that can deal with object in 2D image spaces. And here the motivation, the main goal is we want to develop a object-oriented representation, and we want to do it in an unsupervised way, and we want that representation to be interpretable, so like what and where, things like that. And this model can learn representation through the encoding part, and then it can also generate, do rendering, so we can generate some synthetic images. And we develop this model on raw image only. So there is some previous works working on this kind of unsupervised vision thing. So one approach is called object attention-based approach. Here we are given image, and we try to attend some local area and treat that local area as the object area. And the other approach is based on scene decomposition. So in this approach, we have this final scene, and this model try to explain this final scene as the composition of different mixture component. So this is one component, this is another component, and by mixing all these components, it can explain the whole scene. The main difference is here we only attend on local area, so this system is pretty difficult to capture. Maybe not every object is like a local, well shaped. Maybe some object is has very different shape that is difficult to make this kind of bounding boxes. And also, if there is a complex background, it is pretty difficult to model that background. So in this mixture model, it's more flexible. So you can deal with this kind of thing and this kind of thing, but it doesn't really have a object-wise representation. So in that sense, object object-wise representation, this is better, but this is better in terms of covering the full image with like very difficult morphological area as well. So this is one previous work that works on this kind of image. And as I said, it can deal with object-wide disentanglement well. But main limitation is it scales really poorly. So current state of the art is like dealing with this kind of 2 or 3 MNIST digit object. So detecting this thing without supervision. And yes. And this is the follow-up research that try to improve this scalability problem of previous model error. This is spare, so it actually improved scalability up to around 10 digits. So you can do that detection thing pretty well. This is the previous system, it fails. And it can be applied this kind of Atari game, but because you cannot deal with the background, as you can see here, this part is actually considered background, but it detected as a small object areas. And this is the other approach based on this scene mixture. So as you can see here, this is full image, and this model try to explain the full image by combining as a mixture of different components. So as you can see here, it looks like object-wise if you only see this part or this part, but it's actually not. So this thing, and this thing, it is pretty difficult to consider this as a kind of object representation. So yeah. So the summary of these two approaches is attention-based approaches. It cannot deal with the background or morphologically complex object well. But scene decomposition approach, you can do this well. But this approach is good to get object-wise disentanglement. But scene decomposition really doesn't have that thing. And both systems are really scales poorly. And we process our model, which is called SPACE, spatially parallel attention and component extraction. And our model, we try to achieve all of these important criteria. So our method basically to combine the previous two approaches in a principled probabilistic modeling framework. And we also achieve making it very fast by making it parallelizable very well. So the model works like given an image, we have this object attention path, and here we have also scene decomposition path. So the high-level idea is we distinguish foreground and background. And foreground, we want to deal with this local object area, and we want the background to explain morphologically a complex component, something like this. So this path deals with background, and this path deals with the foreground, and it can make the final image. So this is some generative process we do, but I think this is not very important here. And this is some experimental result. So this is the full target scene, and this is reconstruction because our model can generate. And this is the foreground from our model and background, and these are background decompositions. And this is the comparing baseline model spare. It can also do foreground thing, but it can really, actually it can not do background modeling, but actually we added our own background model for fair comparison. It can do very naively, but it is not this level. And it doesn't provide this kind of background decomposition. And these two approaches based on scene mixture, they really don't have object-wise disentanglement, but everything is explained like as a mixture component. And this is applying our thing to more many object scenes. So you can, if you compare this thing to the previous work, I mean, just 10 MNIST objects without background, this is a pretty complex task, and we show kind of similar result than what is shown in the previous slide. And we also applied this to the Atari games. We can detect object pretty well, good segmentation mask, and good background decomposition. And this is also another Atari game where what is interesting is this background is actually moving background. It's not static. and our model can deal with it pretty well while detecting the foreground objects as well. But other models, we can see that they are failing. And our model is also really fast because we made it possible to parallelize the model. So this is the one iteration time we measured, and this is our model, and this is spare, and these are two other baseline models. So we can see our model is also pretty fast. And the previous one is only one iteration time, and this is the full training time until the convergence. So as you can see here, our model is also really fast than the other models. So yeah, it's fast, and it can detect foreground well, and also decompose the complex background. And it's more practical problem. So in machine learning, many people are working on this thing, and here in this game there's the key here, and that key never moves, always the same position, and its appearance doesn't change. So usually this part is not detected as a foreground. It's always, but in our model, for some reason, it's detecting this key as a foreground. So that's something interesting. And this is a result on other games, also working pretty well. And here we have some video applying our model on other game, and these are foreground, and this is complex background decomposition. And this is on other game where we have a dynamic background. As you can see here, the background is decomposed pretty well while covering the foreground as well. So this is done without any supervision, only from the observation of this image. It's pretty, I mean, to me, interesting that a model can do this thing without any supervision. And also, yeah, the Atari games. Okay, yeah. That was the first model. And the other thing is now, on top of this, we want to add another dimension, the temporal dimension. So in previous model, we applied to Atari, but we made this kind of bounding box, but this isn't really doesn't have the temporal information. We are applying the model every frame again and again, so it's not tracking one object over time. So in this model, we want to do that tracking. So here, the problem, most of the setting is the same as the previous setting, but we want it model the temporal dynamics, and also we want it to be scalable. And we use not only single image, we use a video as data set. So previous work is what is called the square, and in this model we have a scene where task is usually some objects are introduced in the middle of the video, and some objects are also can move out from the frame. So we need to deal with this kind of discovery and propagation of existing object. And this model introduces this modeling, but it also scales really poorly. So it can only deal with like 2 or 3 objects. And it doesn't also cover the background. So this is some demo of that model. So you can see it keeps tracking some object, and when a new object is introduced, it gives a different box. So it is indicating that it is discovered. So even if this looks very simple toys, but the model behind this is really complex actually. So it's really not easy to do this without any supervision. But this is kind of the first thing the human infant like does when baby is born. The basic thing is it needs to learn to track moving object, right? So in our model, we proposed this model called the scalable sequential object-oriented representation. So here we achieved that our model now works nearly 100 objects. Actually, it can be, I believe it will work on even more scales, but we haven't just tried it. And the key idea is, achievement is we also made the model that is fully parallelizable. So at each time step, our computation complex is order 1, while the previous model uses order n computation. N is the number of objects. So this is linearly increasing the computation with respect to the number of objects. And we also introduced this, what is called the proposal rejection mechanism, to prevent this propagation collapsing problem. So yeah, in our model, because we provide very powerful discovery module, and this powerful discovery module tends to try to explain everything, right? So the model tends to try to ignore this propagation part. So to prevent that, we introduce this proposal rejection mechanism where we try to find these are what is propagated object, and these are newly proposed object. And we need to find some matching between existing object, and that needs to be discarded, and only what is remained need to be treated as a new object. So this is the overall architecture of the model. And the result is also pretty impressive. So these are the baseline models, the square. We can only apply it to small scale problems because we couldn't make it even work, so we cannot measure its performance. And this direction is the object density. So here we have between 100 and 120 objects, and these are like a 2, 4, and 10 to 12 thing. So our model works pretty well for all density scales, but baseline model fails as the scale goes up. And for these scales, it just doesn't work. And these are also the counting and reconstruction accuracy. This is our model, and this is comparing model. And this is our model, this is comparing model. Here, the lower the better. Here, the higher the better. And this is some Appalachian study showing what we proposed, this proposal rejection mechanism really works. So when we don't apply this projection rejection mechanism, these are those results without that thing. So we can see that this is propagation rate, and the propagation rate decreases to 0. That means everything still try to discover in every time steps. But with proposal rejection mechanism, we can prevent that problem and actually let the object be propagated over time. And because our model has order 1 computation per time step, so when we increase the number of objects, we stay this kind of computation time, inference time, but the baseline model linearly increases. And this is the total training time. Our model also converges really fast. And yeah, these are some demonstrations. So in the previous slide, I showed you what previous model does, like a 2 or 3 MNIST digits, but now we have like 50 or more than that. And this is original image, this is reconstruction, and this is the bounding boxes, the detection and tracking the object. So we can see that it does things pretty well. And here we have added background, and that background image is actually dynamic. So we can still do that unsupervised detection thing while dealing with this dynamic background as well. And this is actually the first time in this line of research made this kind of model, unsupervised model, work on natural scene data set. So here, this is the actual scene of some, I think, station. And this is people moving, and our model can track each people. It misses sometimes, but in general, it works pretty good. And we can also do segmentation as well. And this is the trajectory. And this is background generation. Okay, so yeah, these are, this is the second model. And this is the third model. Now, in this model, we don't have time, but we have the object and into this space, and we want to learn their relations, more structure among this object. So, so this is the motivation is like given the real world, actually what should be object is not clear, so because object consists of different parts, and maybe some object connected together, so it can be another object. So That raises the problem of what should be the part whole from what we actually observe. And this is like the problem of unsupervised scene graph learning from images. So given only this image, we need to identify that maybe this wheel is part of the whole car, something like that. And this whole car is actually part of the whole scene. This kind of structure needs to be discovered. What computer vision people, what is done in computer vision is they provide all the labels. So this belongs to this belongs to this, and with the segmentation bounding. But we want to learn this kind of structure, scene graph structure, only from the image. So this is the model we propose, which is called rich representation of interpretable and compositional hierarchy. And this is our generative model, the latent variable generative model. And we provide here the structure of the scene graph that should be learned only from this observation. So with this model, actually this is our synthetic data set. So a scene has 4 here objects, and each of these objects consists of many parts. So in our model, actually we can detect object, which is this white bounding box, and inside this white bounding box we have other green bounding box that represent the part. And it also detects other objects. Here this object has only one part, and this object has small 2 parts. So you can detect this thing pretty well. And to do this, actually we introduced some kind of concept memory. So where each cell in the memory should learn some kind of concept, and this we try to explain this scene as the composition of this concept memory. So this is visualization of those concept memory element in that concept memory, and we can see that each memory cell learns kind of the prototypes of the object shown in the scene. And because our model is not only like object detector, it's a generative model, so we can generate after learning the synthetic scenes. So these are generated objects. This is not what is really observed. This is something new, and this is the scene generated using this generated object. And yeah, we also applied the composite MNIST data set. So this looks simple, but this is actually more difficult than previous thing, because here the definition object is a composition of 3 classes of object, but here the part component 4 or 3 is randomly sampled from a large data set. So there is some variance, even if it's the same object class of 4 and 3, each actual observations, realization samples have actually different appearance. But our model seems to work for this thing as well. And these are also scene generation. And the one motivation of learning this kind of structure, latent structure, is if it is really good model of the world, it should provide good performance to some downstream task that uses this representation, right? So in this case, we after learning the system, we use the representation as input, and from this representation we ask some simple classification or regression task. So if the representation is really good representation of the world or the observation, learning this regressor or classifier should be very easy. So for example, the MNIST case, we can define some task like predicting sum of max digits within each object. So object has many parts, and we first find the max number, and we have different objects, and the task is to sum this max number, so the network needs to predict that. So if we have, because our model already have the object level hierarchy and what is inside that, what's the part, so if you use that representation, this task should be easier than the other model that doesn't have this structure. So this experiment shows that result. Okay, so here in this work, we try to combine this problem of dealing with object, but here now we move to 3D space. So far we observed the image level, but here we want the representation to be 3D representation, which means this representation is viewpoint invariant. So we have one representation, but that representation can provide reconstruction of any different viewpoint. Like my representation of this laptop is not only from this perspective. I can imagine what I would see if I were standing from this point. So we want to achieve that kind of thing here. And actually, previous work have done these two parts, but it doesn't have the time component. So you cannot model dynamic scene. So in this work, we try to do that. So the goal is to learn this 3D representation from, in our case, dynamic 3D scenes, where we have, for example, multiple objects, and those objects are moving the space. And this is the model, what is called the generative query networks, which can do this thing. And in our work, we introduced what is called sequential neural networks, and use this sequential neural network to implement temporal generative query networks. So this is the model. This is a previous model, but we made it the model using recurrent neural networks, so we can make it model the temporal dependency of the scene. So this is also a general framework, not only scene understanding from machine learning perspective. This is a general framework. A model that can do transfer learning and meta learning together. So we call this model as a kind of meta transfer learning algorithm. And yeah, this is a temporal generative model framework. Now, actually these are the same image, but I pretend this is like the objects are moving over time. And so this is some experimental result. We first apply the SMP model to 1D regression. Here, the underlying regression function itself is changing over time, and it can only observe some part of the observations, and this is the prediction. It needs to follow that thing. This is the baseline model, and this is our model. We can see it's following it pretty well. And this is applying the temporal GQM model from some 2D moving object problem. So these are what is provided as a context from which the model can learn, and we actually ask, after observing these context images, if we give this viewpoint as the query, what would it be look like? That's the question. So this is our model, and this is the baseline model, so we can see clearly that our model can do pretty well, and this is ground truth. And the way we see different colors here is this is stochastic model. So there is random noise, so the color randomly changes. So this is actually a good thing that our model can model the color change over time. And this is some visualization. Similarly, this is baseline. We can see that it's pretty makes blurry things. And our model does pretty good job. And this is applying the same model to now 3D scene understanding. Here we have some cube here, and that cube rotate or move in the space. And we placed different cameras from different viewpoint. And because the representation is 3D representation from different viewpoint, it should be able to generate the corresponding images. So this is the true model, and this our model does a pretty good job. And similar result, and multi-object loom, and some quantitative analysis. And this is some result. We go even further. In the previous work, we don't, even if we represent the 3D scene, temporal 3D scene, the representation is not disentangled in object wise. So in this model, we actually disentangle the object representation, and we have a modular independent object representation, so we can change its position and we can render it, and as you can see shown here, you can generate the scene from any viewpoint. So this is a pretty exciting result. Yeah, the following, some works are some more application-wide side of this theme, in this theme. So here we want to add some agent interaction, but this work is also pretty interesting. So maybe some of you know about this, I searched this, and this is called fear box or something. So you cannot see what is there, right? But you need to touch it, and people feel it's scary, and they feel fear, because even if it's input from one sensory, like haptic information, but they visualize and they imagine, right? So in our brain, we really have like a multimodal or modality invariant high-level conceptual representation. And this haptic experience actually requires that representation, and one can visualize what would happen, something like that. So we want to make that kind of models. So one question is, can we touch something, not observing it, and can we actually visually generate it in using 3D representation? And yeah, so the goal is to learn modality invariant 3D representation, and this is our task. We have some kind of cube of different colors and shapes, and we let the simulated robot only touch these blocks, and ask, can you visually generate this block from any viewpoint, right? This is what we humans can do, right? We draw a drawer and put our hand and touch something, and we can find the pen or cup inside there, right? So this is how we generate the data set. We have the real target object, and we have multisensory input. It doesn't need to be only visual and haptic. It can be a texture input, or it can be a speech signal, whatever. And using this, any pair of combination or provide any of modality as input, and we want to generate any of the cross-modal modality. So the representation is really modality invariant. It can generate any modality from that representation. So this is our architecture implementing this, and this is our main experiment. The cubes and the haptic inputs, and this is also visual inputs. And this is the result. In this experiment, we provide only single visual input, and that is from very extreme perspective. So from here, we cannot actually infer the full shape of the object, right? Really difficult. And in addition to this, we let the robot touch that object like maybe 5 times, 10 times. Grab it, try to grab it. And then this is what is generated by the model, and this is the ground truth from different viewpoint. Each shape is exactly same as the ground truth. Right? That's interesting. What is also interesting thing is, for the part what it has already observed, this part, the color is the same as the ground truth, but the part it has not observed, actually it generated a random color based on its previous experience. So this makes total sense. And these are different samples, because our model is a probabilistic model, we can sample. And for different samples, we have different color composition for the part that is not observed. Right? So this is like imagining different possibility after observing only some partial observation. After observing this, I can imagine maybe some Mac has here some sticker or something, but that is kind of possible future or imagination. And here, this is also interesting. We provide this image, and now we increase the number of experience. And when I touch only once, then I partly improve my belief about that target object. If I grab it again from different angle, then I update my belief. So these are the progression of my belief update. So as we keep experiencing more, it becomes close to final target object. But in the early, without any experience, it makes some wrong shape, but the color is also, there's a part of the color is consistent to what is observed. But when it grabs more and more, it converges to better shaping. So this is the other part. After observing visual thing, we try to generate the haptic experience. So we have in our simulator 120 haptic dimensions. So it can also, so it's like after looking at this, if you touch this laptop, what would be feeling, right? So the model actually can do it. So yeah, I think this model is also quite interesting. So it doesn't only need to be visual and haptic experience. It can be sound on object. So I can provide only this kind of sound and then let it visually experience what that object look like. Or we can provide text description, something like there is a cube with 5 blocks and 2 the most right hand side, the cube is like something like, and we can provide this textual description and let it visually generate, or only from this textual description, let it feel what would you feel like if you grab that object. Something like this thing is possible, I think. And the last application is to use this generative model to do another imagination, but that is temporal imagination. The motivation is like this. So in machine learning, we have this model-based RL or model-free RL. Model-based learning, we use imagination ability to plan better. In model-free, without imagination, we just do things well. So, but what we have been in machine learning done is this imagination is very early stage, but the previous model try to imagine like every second level. So it doesn't make sense. If I want to plan the way past I'm going back to my office here, is I don't need to imagine like every time step like a second. I just need to imagine, the past, some abstract, temporarily abstract past how to go to the parking lot. And then from parking lot, maybe I need to stop by a gas station, something like this. So we need to actually imagine in the temporally abstracted dimension. So that is what we try to achieve here. And this is the example. An agent is navigating this maze. And actually here the frame we have red boundary is the point the agent decided to jump for the next imagination. And it corresponds to actually this point, the cross, because while the agent in an aisle, it only just need to move there, so it doesn't need to imagine that thing. And we apply this to some planning algorithm, and with jumpy imagination, this is without jumpy imagination, our method works much better than this second level without jump imagination. Okay, yeah, that's pretty much about I prepared today, and this talk is about why in the beginning I explained why we need to build world models instead of solving each task narrowly. So if we can build this kind of core world model, from that general knowledge we can extend our problem set, and that learning will be much more efficient. And in this thing, I proposed the generative latent variable as the framework, and we try to achieve this unsupervised object-oriented, including time and space concept and agent and relations. And I think, this can be done, be a framework or foundation of learning the common sense, and where we have the modular and causal compositional transferable interpretable representation that can be used to understand the world. Yeah, that's it. Yeah. Thank you.
You can take your own questions. We have plenty of time.
Yeah. Okay. Yes.
So all the models that you described are based on probabilistic generative modeling.
Yes.
So are there any weaknesses to such approach of modeling, and are you aware of any other modeling approaches that address these weaknesses?
So for now, I don't know any other approach that can learn representation only from the observation. So one interesting model is this, maybe this generative adversarial networks, GAN. So that is very famous and popular, and it's in media, like generating really realistic human faces. But that model focuses on making realistic generation, making synthetic data set. But that model really doesn't learn the representation. But in my work, I'm not actually interested in generating realistic scene. So I'm interested in this, like how to perceive the world. So as long as we can build good representation of the world, I use this generation part as a path to get the learning signal and to backprop to learn the representation part. But actually the generation part, partly it is important for this future generation thing. But I think it's not main focus, and the fact that GANs cannot learn representation well. So that is, for now, I think for this purpose, is not a very interesting model to me. And other than that,
maybe non-probabilistic modeling approaches.
Yeah, it's possible. I mean, just use the same thing as a deterministic model, but that I think has clear limitation. Learning deterministic representation. For example, one example is the future imagination. The goal is we want to imagine all, important possible future, but if it is deterministic system, and if it gives me only one future imagination, that is really not very useful, right? So the system, the way why AlphaGo system can beat the human Go player is because it can, in parallel, imagine all the possible strategies of the past, like really scalably. So that's the power of doing parallel imagination. So I think deterministic system really is not good for that purpose. And in general, the world is, I think, is really difficult to model with deterministic system. Right. Yes.
I think there's a really, I'm really interested in the kind of parallel you're drawing at the beginning of the talk between the sort of like structured, the structure that you're building in your models that guides the learning, right? And that is sort of parallel with the sort of core knowledge idea from developmental psychology, right? And at the same time, there's been all these arguments about, or the suggestion that the kind of structure that is learned by just a kind of dumb conv net trained on a bunch of images, right, is somehow recapitulates the structure of the sort of representation in a really visual system, right? So like, which of those is more important for human cognition? And can you have one without the other? And like, at what point do you go from these kind of compositional, modular representations to the kind of more, manifoldy kind of representations that are learned by the ConvNet? And,
Okay. Yeah. So I think that ConvNet representation experiment is it's interesting because they kind of use big ConvNet and then they try to make some correspondence. Oh, this representation really looks similar to what human brain we can represent it. So that's scientifically interesting evidence that what we are doing in machine learning AI is this like a human imitating system actually have one more evidence that it's just similar to what human brain does. So that's one part. And the other part is why learning this representation is important. So there are two aspects. I think one perspective is try to learn representation that is optimized or that provides good performance for the target system. For example, in language, we try to learn very good embedding that is very good for maybe a specific task like a translation. So these representations doesn't need to have structure, or it doesn't need to have some corresponds to real world structure. It just needs to be very optimized vector, continuous vector that provides good performance. But if the metric is if we only care about the target task performance, this is a good approach. But if we ask other questions, can this representation is transferable? Can we do other causal inference from that representation? Then that is pretty different metric, and that is very important metric because we humans can do very well, but current AI system does really bad for that thing. So the structural representation I try to learn here, like object and its relations, more kind of a little more symbolic representation is good for that thing. For example, by definition, I think if we want to do reasoning or causal inference from this natural image, we first figure out the variables. So we need to do variable binding from low sensory input. Once we figure out what is chair and what is person, then after that we can do this causal inference or reasoning, right? So my work learning this structural representation is, in that sense, is important. And another evidence is from so DeepMind achieved good performance for these Atari games. So they achieved superhuman level performance. But it's actually performance of getting high score one specific game. So if we see from that metric, it's a good system. But if we ask different aspect, can the learned policy, if we apply to different game, can it learn it quickly? Even if it's a very similar game, even if we just, there's a paper, there's one Atari game, we just change the color, and the learned policy totally fails. Yeah, but if our system, if the representation is more structured, if it doesn't learn only from the full image, if we disentangle what is object and how those objects interact, then that system should be much more robust to that kind of little manipulation, or the knowledge can be transferred. For example, if you learned from one game that this monster-like enemy or entity, always when my agent hit that thing, then my reward decreases, right? Then we can learn kind of general knowledge. In other game, if we see kind of similar appearance of monster, then we don't need to current AI system without this kind of generalized structural knowledge. It should experience it again and then learn. But we can just simply, with this structure, transfer better, and it can immediately learn that this is something not good to be close, right? So, yeah, so I think there are two aspects of understanding the role of representation in machine learning. You know. Yes.
I have one more question.
Yeah.
Actually, it's a big question.
Yeah.
So I see a kind of trade-off in the prospect of representation learning, you know, especially for these visual tasks. On the one hand, you want the representations to be interpretable, and that sort of means mapping them in sort of predictable ways onto physical quantities. On the other hand, you want the system to be able to discover them, and sort of that means, in some sense, that whatever categories discovered are not necessarily open to inspection by the designer. So this is a kind of famous problem in evaluating unsupervised classification. You get these categories, are they good or bad? The system. And so I'm wondering, you know, particularly as you start getting more fine-grained learning about scene structure, how you see this playing out methodologically. So, like, I happen to have noticed that your scene decomposition doesn't really have any knowledge of light, so it doesn't discount the illumination. It treats shadows as parts of objects where it has them. It doesn't recognize the variation in light that comes from the orientation of the surface and the surface reflection properties. You know, so when people like Josh Tenenbaum do inverse graphics, they have estimates of the material properties, but sort of in order to make that work, they need to have a forward generative model that actually knows about the physics of light. And sort of having that forward model that's knowledge rich is part and parcel of getting, in their way of thinking, parameters for the inputs to the generative process that are interpretable and physically meaningful. But that's not, that's in a lot of ways a lot more supervision than any real machine learning researcher would want to use. So how do you see that playing out? How do you see being able to get something like illumination out of the system without telling it how light works?
Yeah, I think even if what I showed here, we don't have explicitly the model of lighting or other, even we can model time, so lighting changes over time when sunset and sunrise, things like that. We don't explicitly model here, but I believe this latent variable modeling, we have modeled the lighting effect there, and then let the appearance be function of this lighting latent variable and other factors. Maybe the intrinsic appearance regarding, discarding the lighting effect, and let the final observation to be some kind of composition or some function of lighting and the inherent appearance. If you do that kind of modeling, I think based on what I have observed through this line of research, I think will work. So my simple conclusion, if the scene is very complex, I don't know yet, the problem will be more complex, but if I work on that problem, I will start from just single object scene and just put appearance latent and model the lighting latent. So see whether it works in this framework, but I think it will work. So that part, my answer is we haven't just tried, but the framework I think has the potential to that thing as well. The thing is in the design of that generative process, so this is somehow some trade-off between fully learning without any knowledge, really flexible without any inductive bias. We can just put very complex, fully connected neural net and let it, whether it can do this thing or not. But in the design process of this kind of probabilistic model, actually I'm probabilistic programming, I'm just transferring my knowledge into this model. So this is based on, for example, every object should have X, Y, Z 3 dimension, and maybe the appearance is affected by the lighting. This thing is transfer of my prior knowledge into programming of this model. So that part is not learning part, that is designing part. And this thing ideally should be as broad as possible, and because it should be minimally guide what the model should learn. And then the other part, filling inside of this probabilistic programming should be driven by the data. But if this programming part, if that is too broad, like a fully connected neural net, then it cannot learn really. But if it is too narrow, then the system cannot generalize well. So my belief is that there exists really core structure we can use to design this world. For example, like the existence of time, or this rule of object, the cohesion and continuous behavior of object. This thing can be used in the design of this kind of model. So yeah, so that part is the trade-off between design and learning, I think. And I think what Josh Tannenbaum does is, I think their model, he's dealing with more high-level things. So in the bottom, they use more supervised approaches, so starting from maybe already object coordinates. But my work is more I'm inspired a lot by his work, of course. So, but I'm focusing. He claimed about this inverse graphics thing, but his recent work is actually assuming this inverse graphics, and then we can do this. But this inverse graphics part is actually not solved. So pretty much of my work is what I'm doing. Yeah. Yes?
I have a related question on importance of these priors and learning the representations. It seems to me that the strongest prior that you have in your model is that the world exists in a high dimension, but it is composed of low-dimensional representations.
Mhm.
You have a generative model to learn those low-dimensional representations.
Mhm.
So is that prior enough to embody the agents with common sense, as you described in the beginning, in the sense of intuitive physics and psychology? Or would you need more stronger priors? Like one drawback that I can think of with just this prior is that you would need lots and lots of training data, even if they're not labeled. There's lots and lots of training data to train your model. So you have more stronger priors that can possibly discover these laws of physics, intuitive physics. Maybe you won't need as much training data. So what's the role of priors?
Yeah, it's kind of connected to Matthew's question. So, yeah, of course, if you don't provide any prior, or if you provide very weak prior, then learning will require lots of data, or even with lots of data, it cannot learn. So, it's kind of really trade-off between the amount of data we can use and our expectation about how fast it should learn. Even if we have like billions of data set and it can learn it, but if we expect, like we humans can learn it from 10 images, then why AI system doesn't learn from 10 images? Then even if we have billions of images, it's not enough, right? So I think the prior is careful maybe statement. We need to use prior, but that prior needs to be broad as much as possible, or it should be in the right level, or ideally that prior also kind of learnable prior. So some part of it we design our inductive bias, but that inductive bias should not be very hard coded. So it should be flexible. So if we observe more data, this inductive bias is kind of provide the minimum. That's basically the definition of prior. The prior doesn't strongly enforce something. It just provides some kind of roughly guide the way it learns. But and eventually, what we converge to right solution should be based on the data. So that's. So I don't know whether regarding your question. Pretty simple. We need right level of prior, but I don't know what that right level of prior is. Yeah. But there is some discussion. So the professor at the University of Alberta, Rich Sutton, who is the father of reinforcement learning. So he recently wrote some essay about about computation, and I forgot the title, but it's a really interesting essay. So the main message in the essay is what we have learned in the past, the history of the AI. We have made many mistakes. So that mistake was mainly about we need to use human design to solve some complex problem. So for example, in the old days, to solve the chess problem, what we human first tried is like developing lots of rule-based system, but we learned that fails without learning from really data and using the parallelization of the modern computation. If we try to use human knowledge to achieve something, the main message of his article, we eventually always failed. So what it says is we should not try to use that human knowledge in the design of the some AI algorithm, but it is so many people against to it, and I'm also one who are against to that perspective to some extent. So I think without prior knowledge, I think we can not learn even AlphaGo system or any system, even CNN is actually reflecting human knowledge about how visual system works. This local receptive field, this kind of design is a reflection of human understanding in the design of the system. So I think what he really intended is we should not try to design the solution, but we should try to use our knowledge to design some kind of meta learning algorithm that can something like CNN is kind of that thing. So that is not directly designed for that solution, but that is designed to by some human knowledge to solve many problems and generalize well.
Thanks.
Yeah, thank you.